This video is for Chemistry in the Earth System, Unit 2.2, Arrangement of Electrons in the Atom. Today's essential question: how did quantum theory help establish a relationship between the energy of an electron and its position in an atom? First main idea: from Bohr's model to quantum theory.
In the early 20th century, a Danish scientist called Niels Bohr began to study the properties of atoms. Following on from Rutherford's discovery that the atom is filled with empty space, Bohr wanted to understand why it was empty and why it didn't collapse. Rutherford had developed a model of the atom that was like a solar system, with the nucleus at its center. Bohr took this idea and added something completely new: quantum jumps. In contrast to Rutherford, Bohr stated that instead of having random orbits, electrons occupied very specific energy levels. Bohr described the atom not as a solar system, but as a multi-story building, with the nucleus on the ground floor having the lowest energy, and the electrons occupying the floors above. Sometimes the electrons would jump from one floor to another. This is what he called a quantum jump. Bohr's model of the atom was groundbreaking. It described how electrons move in defined orbits around the nucleus, with each electron in a specific energy level. His theory also enabled scientists to explain how atoms absorb and give out light. Bohr's model was also the beginning of quantum theory and paved the way for the work of other great physicists such as Erwin Schrödinger and James Chadwick.
So Bohr's model of electron arrangements in atoms had serious flaws. It applied to only one element, hydrogen, for example. It also incorrectly described electrons as moving in fixed circular orbits in an atom, which is not necessarily the case. Although Bohr's work showed that electrons had discrete energies, each electron's movement could not be easily defined. A scientist named Werner Heisenberg discovered that it was not possible to describe both the velocity and location of an electron at the same time. Then this concept became known as the Heisenberg uncertainty principle. According to the Heisenberg uncertainty principle, electrons cannot be described by precisely defined movements. Instead, it is only possible to describe regions surrounding the atom where that electron is most likely to be found. So a new theory of atomic structure began to develop as a replacement for the Bohr model. This theory is called quantum theory, or quantum mechanics. In this theory, electrons occupy discrete energy levels, as Bohr proposed. However, instead of traveling in fixed orbits around the nucleus, electrons are found around the nucleus in regions of space called atomic orbitals. An orbital's shape and size are defined by the probability of finding an electron in it. Thus, electrons are not pinpointed to exact locations. Instead, they have only a probability of being found in certain regions. The term electron cloud is often used to refer to such possibilities. Quantum numbers. Quantum theory uses quantum numbers to describe the electrons in an atom. There are 4 quantum numbers. Each electron in an atom has a unique set of 4 quantum numbers. So each electron in an atom is assigned its own set of quantum numbers. The first 3 quantum numbers describe the probable location of the electron. The 4th quantum number describes the spin of that electron. Taken together, the set of quantum numbers for any electron describes the amount of energy found in that electron.
In the early part of the 20th century, scientists found it difficult to understand the structure of atoms. Ernest Rutherford and his colleagues visualized them as negatively charged electrons circulating about a positively charged nucleus. A German physicist named Max Planck suggested that energy emitted or absorbed by an object could only be emitted or absorbed in discrete amounts or units. He called these units of energy quanta. Niels Bohr, a Danish physicist, visualized atoms much like our solar system, with the nucleus like a sun and the electrons orbiting it like planets. This is called the planetary model. He then applied Planck's idea of quanta to the behavior of the electrons surrounding the nucleus. He suggested that electrons' orbits depended on their amounts of energy. When an electron absorbs energy, it jumps from an orbit close to the nucleus to one further away. When an electron moves closer to the nucleus, it emits energy. In both cases, the energy is only in discrete quantities. Louis de Broglie, a French physicist, proposed that electrons were not only particles, but also a form of energy that acted in a wave-like manner. But the more evidence that was gathered, the more scientists came to understand that atoms were not like the solar system at all, because the electrons did not circle the nucleus in regular orbits. In one of the most significant developments, in 1927, Werner Heisenberg, a German physicist, showed that it was impossible to determine the precise location and velocity of an electron at the same time. All that could be done was to describe the probability of the location of electrons. This has come to be called the uncertainty principle. All of these ideas have come together into what is now called quantum theory, or quantum mechanics, one of the most important scientific advances of the 20th century.
Now let's get into the individual quantum numbers, starting with the principal quantum number. The principal quantum number, which is represented as a lowercase n, indicates the energy level in which an electron is found. Values for n are integers starting with 1 and then continuing upward. So n can be 1, 2, 3, 4, 5, and onward. The principal quantum number corresponds to the periods of the periodic table. Each period from top to bottom on the periodic table represents a new energy level and an increase in the principal quantum number. The azimuthal quantum number. In general, the azimuthal quantum number, which is represented as a cursive lowercase l, indicates the shape of the orbital in which an electron moves, the shape. You might sometimes see it called the angular momentum quantum number or the orbital quantum number. Values for L are integers starting with 1 and continuing upward. But instead of using a number, a letter is used to represent the azimuthal quantum number. So we can say that L can equal 0. L can equal 1, 2, 3, 4, and onward. However, we can also associate those numbers with letters. So as we can say L is equal to 0, we can also say that L is S. L is P, D, F, and onward. So the shape of an orbital depends on whether it is an S, P, D, or F orbital. In this model, S orbitals are spherical, and P orbitals are shaped like dumbbells. The shapes become much more complex than these two examples once you enter the d orbitals and beyond. For any given electron, the value of the azimuthal quantum number is always dependent on the principal quantum number, n. The value of L ranges from 0 to n is equal, 0 to n minus 1. The magnetic orbital quantum number. The magnetic orbital quantum number, represented by m, or m sub L, provides the orientation of the orbital shape along the x, y, and z axes. Values for m sub L are positive and negative integers that depend on the azimuthal quantum number. The value of m sub L ranges from negative L to positive L. The magnetic orbital quantum number is bounded by the absolute value of its azimuthal quantum number. Got a little excited with keyboard there. Yep, sorry about that. The last quantum number, the magnetic spin quantum number. So far, 3 quantum numbers describe the orbital in which an electron is found. These numbers designate the energy level, shape, and orientation of an orbital. The 3 numbers do not completely define each electron in the atom, however. This is because each electron also spins. An electron can spin in a clockwise direction or in a counterclockwise direction. A maximum of 2 electrons can occupy one orbital. The physicist Wolfgang Pauli postulated that the 2 electrons spin in the opposite directions. One electron spins clockwise and the other spins counterclockwise. So, the magnetic spin quantum number, designated by an m sub s, or sometimes just an s, indicates the direction of spin of each electron. Here, there are only 2 possibilities for each given electron. Either the electron is spinning in a clockwise direction, or it is spinning in a counterclockwise direction. This condition leads to only 2 possible values for the spin quantum number, -1/2 or +1/2. Thus, according to the Pauli exclusion principle, no 2 electrons in a given atom can have the same set of all 4 quantum numbers. At this point, you should be able to generate a full and complete response to today's essential question: how did quantum theory help establish a relationship between the energy of an electron and its position in an atom?